You know, every single time you refresh a social media feed or stream a movie or just buy something online, you are interacting with this massive invisible world of systems. Today, we're going to pull back that curtain and take a look at the incredible architecture that actually powers our digital lives. I mean, really think about it for a second. You click a button, and almost instantly, this beautiful, high definition video just starts playing, probably from a server that's thousands of miles away. It feels like total magic, right? But it's not. It's actually this whole chain of brilliant, interconnected solutions. And let me tell you, when you start to unravel them, you realize just how incredibly difficult the problems are that they're solving. Okay, so here's our game plan. We're going to start small with the digital blueprint of just a single video file. Then we'll zoom out and tackle the data highway problem, how to send it. After that, we'll meet the digital traffic cop that manages the flood of requests and see how a global delivery network gets that video right to your screen. And finally, we'll get to this deep, fundamental, impossible choice that every single engineer has to face. Let's get into it. So our journey starts with the most fundamental piece of the puzzle, the digital blueprint. How is a video file even packaged up so it can make this incredible journey across the internet in the first place? Well, the secret ingredient here is something called a video codec. You need it because, get this, uncompressed video files are absolutely gigantic. So a codec is kind of like a super intelligent digital shrink wrap. It compresses the file down to a size that's actually manageable for streaming, and then your device decompresses it on the other end so you can watch it. And right away we run into this classic battle in the tech world, the new flashy thing versus the old reliable one. On one side, you have the newer AV1 codec. It's amazing, it saves about 30% in bandwidth, and it's free to use. But on the other hand, the older HEVC codec, well, it just works on way more devices, which is absolutely critical for something like live streaming. It's the perfect example of a trade-off, pure efficiency versus making sure everyone can actually see the video. And this really shows you a key truth about technology. Just because something is newer doesn't mean the whole world adopts it overnight. The reality is, a ton of the services you use every day are still running on codecs that are decades old. Why? Because they're dependable. They just work, period, on pretty much any device you can think of. Okay, so our video file is packaged up and ready to go. But now for the really hard part. We have to actually send it across the internet. And this brings us to our next challenge, the data highway problem. All right, here's a question that has probably driven you crazy at some point. You pay for that super fast internet, you run a speed test, and it says you have tons of bandwidth. So why does your video still stutter and buffer sometimes? It just doesn't seem to make any sense, does it? Well, the problem is that video data isn't a nice, smooth river. It's lumpy. Think about a big action movie. A huge explosion, that's a massive chunk of data. But then a quiet scene with two people talking, that's just a tiny little trickle. This herky-jerky stop-and-go rhythm completely confuses the network. It literally gets tricked into thinking you have less bandwidth than you really do. This whole thing is called video bitrate undershooting, and it's a huge reason you see that dreaded buffering wheel. But what if you could teach the network to understand that lumpy rhythm? What if you could make it smarter? Well, some researchers did exactly that. They developed a new method called CAMEL, and the results were incredible. A 14.1% reduction in stalling. That's huge. And it proves a really important point. The fix wasn't about more bandwidth. It was about being smarter with what we already have. And that smarter approach is called frame level control. So instead of just blasting data out in one continuous kind of dumb stream, it sends it in these short, intelligent bursts that perfectly match the actual size of the video frames. It's like it's dancing with the data's natural rhythm instead of fighting against it. Okay, let's zoom out again. We've packaged the file, we've figured out how to send it smoothly, but what happens when it's not just you watching? What happens when it's millions of people all trying to watch at the same time? Well, now you've got a flood on your hands, and you need a way to manage it. You know that feeling? Tickets for a huge concert go on sale, you're hitting refresh like a maniac, and boom, the website crashes. This is exactly why. It's the digital equivalent of 1,000 people all trying to smash through a single doorway at the exact same time. It's pure chaos. And that one little doorway? That's the server. It just gets completely overwhelmed. So the solution isn't to build one gigantic doorway. The solution is to have lots of doorways and a traffic cop out front. In the digital world, that traffic cop is called a load balancer. It sits in front of a whole team of servers and just directs traffic. It sends one request here, another one there, making sure no single server gets buried. So how does this digital traffic cop decide where to send everybody? Well, the simplest method is called round robin. The first person in line goes to server A, the second person, server B, third to server C, then it just loops right back to the beginning. It's clean, it's simple, and it works great as long as all your servers are basically identical. But what happens when there's so much traffic that even the load balancer can't keep up? Well, you have to wait in line. And this is just wild. The math that powers those virtual waiting rooms we all hate, it actually started over a century ago. In 1909, this Danish engineer named Agnar Erlang invented something called queuing theory because he was trying to figure out how many telephone operators Copenhagen needed. Decades later, his work was absolutely essential for building the ARPANET, which of course became the internet. Crazy, right? So far, we've pretty much been talking about systems in one location. But the internet is, global. To get content to you fast, no matter where you are in the world, we have to find a way to close the physical distance. This is where a content delivery network, or CDN, is a total game changer. Just picture a massive, globe-spanning web of servers. So instead of your request having to travel all the way to a single server in, say, California, the CDN has already stored a copy of that video on a server that's way, way closer to you, maybe even in your own city. And this is a huge win for everybody. The content owner, like Netflix, saves a fortune on bandwidth costs. And for you, the viewer, videos and web pages load so much faster because the data just doesn't have as far to travel. The CDN automatically figures out which server is closest to you, they call it an edge server, and sends your request there to give you the best, fastest experience possible. We've now arrived at our final and most abstract layer. All of these different pieces, the codecs, the servers, the load balancers, the CDNs, they all fit together to build these absolutely enormous systems. And when you build on that scale, it forces engineers to make a truly impossible choice. These massive systems, made up of thousands of computers all working together, are called distributed systems. To you and me, when we use Google search or our online bank, it just feels like one seamless machine. But behind the scenes, it's this incredibly complex, coordinated dance happening between all these different parts. And this is where that impossible choice comes into play. It's formalized in something called the CAP theorem. It says that in any distributed system, you get 3 guarantees that you want, but you can only ever pick 2. Those 3 are consistency, meaning everyone sees the exact same up to the second data. Availability, meaning the system is always online and ready to respond. And partition tolerance, which just means the system has to keep working even if parts of the network break. Now, here's the kicker. Partition tolerance isn't really a choice. The internet is messy. You have to build for that. So the real agonizing choice is always between consistency and availability. You can't have perfect versions of both, ever. It's been called the Great Pick 2 of computer science for a reason, and it's a choice you see everywhere. Think about an online bank. They will always choose consistency. They would much rather their ATM network go down for a few minutes than ever risk showing you the wrong account balance. So I want to leave you with this final thought. The next time you're using an app and it feels just a little bit sluggish, but the information it shows you is perfectly correct and up to date, just remember the CAP theorem. Ask yourself, what impossible choice did an engineer just make for me? And the answer is they almost certainly sacrificed a little bit of that instant speed, that availability, to guarantee that the data was perfect, the consistency. It's a completely invisible trade-off, but it's one that's being made for you every single second you're online.